We're now being recorded. So I'm really pleased to introduce Andy Hales to this is the third session for this year's simulation summer school. Andy's an assistant professor at University of Mississippi, who, in addition to doing things like statistics and simulation, is also a social psychologist looking at ostracism, which we're going to try not to do to you today. So I'll try and keep in contact with you on the chat and things like that. And yeah, I guess I'll just hand it over to Andy.
All right. Well, thank you, Oliver. I'll just go ahead and share my screen here and we can get started. So hopefully, let's make sure I do this right. Okay, so hopefully you can see my screen now, including PowerPoint slides are up. We'll just go to full screen here. All right, so I'm excited to talk about power analysis in regression using simulation today. We're going to be switching back and forth between these slides and R. So I'll try not to do it too much, but you'll see as we go that's going to enhance our understanding. Okay, so let's start with just really big picture perspective of what I'd like to accomplish in the hour and a half that we've got here today. This is a workshop, so I'm going to go ahead and borrow that analogy for just a minute here and think about building tables as if we were in a workshop. So you can build a table. I assume, I'm actually not an experienced woodworker, but I assume you could do it relatively quickly without much concern for how it looks, focusing on making sure it's stable and that it does the things it's supposed to do. But of course, you could also customize it to your specific tastes, interests, and needs. And that is a separate additional set of skills. So today, we're focusing on building a sturdy table. With time at the end, depending on how it takes to go through things and what's left over, we can look at customizing to your specific needs and some of those additional things you might do to make not just a table, but your table that perfectly matches your needs. And the beauty of this simulation approach is that it's extremely customizable. But of course, that's no good if the table doesn't stand up. So we're starting with that today. So in terms of an agenda, our mission is to understand how to simulate power analysis for regression. So I'm assuming that you've encountered regression before, but we'll have a very brief review just so that we've got a little momentum behind us and we're reminded of the terms we're going to be dealing with. And then we'll start with a single basic table. We'll simulate power for a simple regression case where we have one predictor used to estimate an outcome variable. From there, we'll scale up and look at how to calculate power for a design involving multiple terms as predictors and combining them to test an interaction. And then, as I mentioned, with whatever time's left over, we might look at different ways to customize. So the packages we'll be using today, the tidyverse for manipulating and visualizing data. I'm going to be showing a lot of graphs from ggplot. I'm going to be showing them. You'll see the code for it, but explaining that is just beyond what we can do today. So thank you for your understanding. And then, Broom will use to sort of clean up the regression output in a way that makes it a little easier to simulate. For our actual simulations, we'll use our norm, which we learned from Oliver on Monday, the basics of that. And we'll also, for generating categorical variables, we'll use this new sample function that I'll tell you about. If you haven't already accessed them, these slides and accompanying code are available at this OSF link. There are two code files on there. One is a gigantic script for basically documenting everything that's in these slides. That won't be very helpful today, but it's there in case you want it. And then there's another one that I think is called working examples or something like that. If you feel like pulling that up to follow along, you can see that's got the essential code that we'll be using to generate our example simulations. Okay, so I won't belabor the value of power. I assume if you've made it this far into the workshop, you care about power. It is important. It helps us avoid waste. One underappreciated aspect of power sometimes, we think of running a power analysis so that we can jettison a study that is destined to be underpowered. But I'm also an optimist sometimes, and I think an underappreciated value of power analysis is that it can flag for you cases where your sample is bigger than it needs to be. If you're taking a sledgehammer to a fly, and you're dealing with a likely big effect size, a power analysis could alert you ahead of time that you'd still have a really high chance of detecting an effect if you had a smaller sample. Now, it's a good problem to have. It's probably not the norm. It's probably more of the exception, but it's nice to be aware of. All right, well, why regression? Regression is a very flexible framework for analyzing both continuous and categorical variables alone and in combination. So if we can learn some basic tools for how to simulate power for regression analysis, it becomes manageable to scale up our designs and also our simulations to reflect basically arbitrarily complex regression models. If you can do it in regression, you can simulate power for it in R. Okay. All right, so I'm going to back up here and make sure, I think some questions or comments are coming up, and I should have done this before, but let me make sure. It seems I can't see the chat when I'm sharing screen.
Hey, Andy, there aren't any questions at the moment. That's just me throwing up the OSF link repeatedly. So at the moment, I can't see any questions.
Okay, good. Thank you. All right. Okay, so there are different approaches to power, and we're going to take one specific path today. So with power, you have an effect size, a sample size, and the probability of detecting an effect. And based on any two of these, you could calculate the third. Today, we're going to be assuming or inputting given effect sizes, or rather regression parameters. And we're going to also be assuming or inputting various sample sizes that we might be interested in running. And then from those, we'll calculate the power that that study design would provide for us. So I'm assuming here that we're doing this ahead of running a study. You're essentially asking yourself, if I run 200 people under these assumptions, what's the probability of a significant result? Or if I run 300 or 400 and so on. All right, and one final caveat before we dive into regression here. I'm using artificially crisp examples here. The effect sizes that we'll be looking at are somewhat fanciful. I think that's helpful for illustrating some of the basic concepts that we're looking at today. And I trust all of you, though, to appreciate that the real world is much more complicated and messy than the clean examples we'll be looking at here. As always, when you're planning for sample size and power analysis, pessimism is wise. It's tempting to become really optimistic and assume that you'll have less noise than the universe actually contains, or that your effect size is especially likely to be very strong when in reality you're not special. Maybe your effect size isn't as strong as you think it is. So try to be intelligently pessimistic about the sizes you put in. So, all right, that's my disclaimer. Okay, so just a brief reminder on regression analysis, what we're doing when we analyze a data set using regression. At its core, it is just a linear prediction. So I'm sure terms vary by geography and by school system, but when I was in middle school, this was taught as y equals mx plus b. It's just a line. It's just a constant and a slope. And if you know the constant and you know the slope, if you were given any value of x, you could predict any value of y. So let's look at this with a more concrete example. Let's imagine today that we're interested in predicting levels of happiness. And we suspect that self-esteem might be a predictor of happiness. I'll just mention as another disclaimer, I've picked these variables arbitrarily. I've picked the hypothetical effect sizes also arbitrarily. Please don't take the specific slope or correlation size or anything like that too seriously. I'm just trying to use some illustrative data here. So just take it as a given that this is the result of a small pilot study where we measure self-esteem and happiness and see if self-esteem helps us predict how happy people are on average. So using regression, the idea is that if we know someone's level of self-esteem, imagining here that it's measured on a scale from 1 to 7, happiness also measured on a scale from 1 to 7, we should be able to predict happiness more accurately. So we construct an equation, or rather our software constructs an equation for us that allows us to do some simple arithmetic to compute predicted values of y given particular values of x. In this case, x is self-esteem and y is happiness. So with this hypothetical example of a very small data set, we could compute an intercept value of 2.8. Now, the intercept is the value of our y variable that we would predict when our x variable equals 0. Now, you might be uncomfortable right now noticing that 0 is actually not a plausible value for our 1 to 7 scale. Because of this, the intercept, depending on how you scale your variables, is often not a particularly directly interesting parameter, but it is part of our equation, so we notice it and appreciate that. The second parameter that we're really interested in our equation here is the slope. This is often the heart of what we're looking at here. What the slope tells us is, on average, for every 1 unit increase in our x variable, how much of an increase would we expect corresponding in our y variable? So in this hypothetical example, our line has a slope, and the slope is 0.21. That tells us that on average, for every 1 point increase in self-esteem, we would expect about 1/5 of a scale point increase in happiness. So as self-esteem goes from 4 to 5, we'd expect happiness to go from whatever this is, about 3.5 to about 3.7, rounding approximately here. So just an extra 2.1 happiness points for every 1 unit increase in self-esteem. Okay, so if we know our constant, which in this case is 2.8, and our slope 2.1, for any value of x, we could predict a value of happiness. So for example, say somebody takes our scale and they get the lowest possible value, which is 1. That's below our sample minimum here, so we should acknowledge that we're extrapolating, but 1 is a possible value for our scale. We can do some simple arithmetic and compute that someone with a score of 1 of self-esteem would have a happiness score of 3.01 on average. We could run the same arithmetic for someone with a score of 2. We'd predict a score of 3.22. Same for any value of x that we might be interested in. Here I'm just going up the integers through our 7-point scale. So for example, at the extreme end here, someone with a score of 7, we would predict that their happiness level in this made up data would be happiness of 4.27. Okay, so if we know the constant and the slope, we can predict a line. That's going to be the foundation of the simulations we run later to compute what our power is for a regression. Now, again, you might be kind of uncomfortable here noticing that there's this error that I've just been conveniently ignoring. Well, we acknowledge that the world is messy, and we can see with our own eyes that the points we're estimating here in actuality don't fall exactly on our regression line. There's error. Some points are overestimated, other points are underestimated. And so we call these residuals. So for example, this participant happens to have a self-esteem score of 2. So we'd predict that their happiness score would be just north of 3 here. In reality, their happiness score is 4. So this person, the model is off by about 0.74 units. So the residual here is 0.74. So we've got residuals all over the place. Some of them are negative. The model can predict higher scores than what you actually observe. Some are positive, like this score is about half a scale point higher than the model would predict. So we have all these residuals. We acknowledge the error. Now we can summarize all of these in a convenient summary term called the standard error of the residual. Now, if you've been taking statistics for a while, standard error can start to sound like water, like a term you've heard so many times it's lost its meaning. But I'll just remind you, a standard error is exactly what it sounds. It's the standard amount of error you would expect the points to be away from the model predicted value. You could think of it as a typical error or approximately an average error. So in this hypothetical example, it just so happens that the standard error across these many points comes out to 0.74. So we have a sense of what the typical error is in this example. Now, conveniently for us, regression assumes that our errors are normally distributed and that a normal deviation from our model's prediction is about 0.74. Now, that's going to help us later when we simulate our own data sets to use that as an input for how much noise we'd like to have in our predictions. Okay, finally here in our brief tour of regression, I'll just remind you that we're looking at a very simple case of regression here, but regression is beautiful because it can handle multiple predictors. So you could predict happiness not only from self-esteem, but from, say, 2 variables, taking gender into account, where gender might be coded as 0 and 1, or you might look at other continuous predictors. Say Z here, we might estimate height is a predictor of happiness. Tall people are happier because they can reach all the things that are high up. So, so multiple regression has the capacity to handle multiple predictors. And we want to keep that in mind when we build our simulations to do so in a way that takes advantage of this flexibility and calculates power, not just for the term that we're interested in primarily, but also for all the terms that we're going to be including in our model. It might be useful to know power for all these multiple parameters at once. Okay, so we know what regression is, and we're ready to run a study using regression, and we'd like to simulate a power analysis. The basic steps are shown here. First, we'll focus on simulating just a data set. For simulating this data set, we'll want to use deliberate parameters. Here, I'll imagine that we have some pilot data informing the parameters we put into our simulations. So you generate your data set. You analyze it for significance on whichever regression terms you're interested in. And then you do that again and again and again and again. And you can summarize those results, and the proportion of times that you observe a significant result under the assumptions you entered, that is your power for any given term. So we're going to start here on simulating a single data set, analyzing it for significance. For now, just trust me that doing this many, many times is possible. We'll use for loops like we did on Monday with t-tests. So we'll table that for a moment and just focus on simulating one data set, because it's really at the heart of understanding how simulation power analysis works for regression. Okay, I ought to stop here and see, are there any questions in the chat that I've not noticed?
Not at the moment, but if anyone has any questions, now would be a good time to pitch one if you've got anything. on Teams you can see when people are typing, but not on Zoom. So if you are typing, I'll give you a few seconds.
Okay.
No, I think that's all good.
Great. All right. We're going to simulate power. That means we're going to be generating random samples. Now, you might be wondering, in a regression analysis, what actually gets randomized? This is kind of abstract, and overcoming this point of confusion for me was a really big moment in starting to understand the essence of this approach. So the question is, what actually gets randomized? The answer is, well, kind of everything. A lot of different things in our model get randomized, but randomized within the constraints of the parameters we provide. So for our independent variables, what that means is we might posit a continuously varying variable with random scores based on some population mean and standard deviation. So we imagine a population maybe with a mean of here 0 and a standard deviation of 1, and we sample from it. These little bumps here represent scores that we could use our norm to very easily sample hypothetical scores from an imaginary population with this distribution. So we randomly generate our X, our predictor variable. We could also do this if our predictor variable were categorical. We could randomly assign people to be in one group versus another. If this is a traditional experiment where we have two equally sized groups, we could just set the probability to 0.5, and as if flipping a coin, randomly categorize people in a group. We'll use the sample function to do that. Where things get a little more interesting and surprising is with the dependent variable. Now, the dependent variable, we don't simulate out of thin air. Instead, what we do is we calculate it based on our simulated independent variables. So this should make some sense. I mean, after all, it's our dependent variable. It depends on our independent variables. So first, we'll simulate our independent variables, and then we'll calculate our dependent variable. Now, we'll do that assuming the parameters that we deliberately enter into our model. But we also need to acknowledge that our dependent variable, y, it won't perfectly match our model. So we got to add some noise to it. And so we'll add a very deliberate amount of noise to deviate from the predicted model. So to go back to our trusty regression equation, what this means is that our constant and our slope coefficient will be determined by u. So you will intelligently select values of these parameters, maybe here based on hypothetical pilot data. You might do this based on well-informed theory. In my experience, pilot data is really the most convenient way to do this. Often it's easier to actually collect some pilot data than it is to speculate about what these values would be in the absence of some pilot data. So you enter predicted values of the parameters, and then you simulate values of X and amounts of error. And from that, you calculate a Y variable. That's the dependent variable. It depends on what you've simulated. That's the approach. Okay, so for the example we're going to do today, assume that we've run a pilot. In practice, if you run a very small pilot, the estimated parameters from that are, if you run 20 people like I'm doing in this hypothetical example, you're going to have really wide confidence intervals. And so you won't have an excellent sense of what these parameters might be. But to get off the ground here, let's assume that these are reasonable estimates. And the approach I'll show you here allows you to adjust not only your sample size, but also different parameter estimates so that you can see under different assumptions about the population, what power would you have. So hypothetically, this is a data set that we can imagine having collected with 35 participants. So this corresponds to the scatter plot we were just looking at. Well, remember that. And so in R, we can fit a linear model. And here we're assigning it to an object called pilot_model. We're summarizing it. And the model gives us a lot of information, but for purposes of simulating power, we're interested in the intercept and the slope for self-esteem, and also the typical degree of error, the average residual that we would expect our model's predictions to be off by. And so here these match the line that I showed earlier for that scatter plot. And we can take these inputs and remind ourselves there's our regression line. All right, so let's simulate a data set. For starters, we'll want an independent variable. In our example, this is self-esteem. I'm just going to call it X moving forward because that's just a little more convenient and universal, but we could name it whatever we want in R. So we'll use the R norm function. We'll assume 100 observations with a mean of 5 and standard deviation of 1. And so we can make a histogram of that. We'd see we have some variability around the mean of 5. This is review, but we've got an independent variable now. So we're off to a good start. So that's our independent variable. For our purposes, we're going to put that in a data frame. We'll get into some of this in just 1 minute when we switch over to R. But this is where things get really beautiful here. So we've calculated X. We have that. These are our values of X. Next, we want to calculate Y. And remember, Y depends on our independent variable. We have our regression equation, and we want to simulate data sets where our values of Y are what the model would predict on average. So let's start one step at a time, entering each term of our model incrementally. So the first term of our model is an intercept of 2.80. For someone who has a self-esteem score of 0, we expect their Y value to be 2.8. So we'll apply that to everybody. We'll give everyone in our sample the constant. That's what it means to be a constant. Everyone gets 2.8. Now here we're plotting our X variable, self-esteem, against our happiness variable, which is currently just the constant of 2.8. You can see X varies, Y does not. Now we want Y to vary, and we want it to vary as a direct function of X. So next we can add our predictor term. So for each participant, we compute their score on X multiplied by the provided slope of 0.21. And now we have a model where our dependent variable changes as a function of our independent variable. This is a perfect line. This is exactly what our model predicts, ignoring the pesky error. So we can compute regression, just like the line says we ought to be able to. All right, now here's where the miracle happens. So we know that the line predicts values of Y as a function of X, given a constant and a slope, but we also know that we're going to be wrong sometimes. So we need to add some error. How much error? Well, let's add the standard residual error. So in our observed model, that was 0.74 was a typical error. Now, just to visualize this, if you're taking notes or doing anything else, now's a really good time to look at the screen. Instead of going straight to the actual amount of error we're going to have, I'm just going to slowly turn the error knob up. I'm going to add an error term. I'm going to do it just the smallest amount at first. We're going to add R norm with a mean of 0, a standard deviation of 0. So here I've added no noise, but I'm going to add just the tiniest amount of noise, just 0.02 standard deviations. Because the mean is 0, half the scores will be over-predicted and half will be under-predicted, but on average, they'll fall on our line. Let's make that standard deviation a little bigger, 0.05, getting somewhere. All right, with 0.25, it's starting to look like a real study. With half a standard deviation fluctuation around our predicted model, we can still discern a positive relationship, but clearly we've got some noise here, and it's noise that we can deliberately dial up or down. We could go all the way up to 2 standard deviations on average. There, things get very, very noisy. So we have control over the degree to which values fluctuate away from our model predicted values. So let's just bring it back to what our pilot data suggests, which is a typical error of 0.74, which would be a scatter plot looking something like this. So that's the essence of what we're doing. Just like with our X variable, here are the mechanics of how we would actually, in this case, we'd use mutate from the dplyr package to create a new variable called X, which is just a mathematical function like we just outlined. So I'll switch over to R. I see there are questions, so now's a good time for me to take a look at those.
Can you access them okay, Andy?
Yes, I can see them now, but for some reason I can't while I'm sharing the screen.
Oh, okay.
Must be an error on my end, but why are you assuming it comes from a normal distribution? The answers so far seem to be addressing these pretty well. So we're assuming our independent variable is normally distributed, but this is correct that the actual assumption is that our residuals are normally distributed, which we're also assuming here. I'm assuming normal independent variables for simplicity for now. Later, we can look at ways to add skew to that, although I'm not certain that I have a perfect grasp over how to do that. So for now, we'll just keep it easy with normal variables. Yes, yeah, the residuals are assumed to be normally distributed, and there we will protect that assumption. Okay, into R. Okay, so using the tidyverse and Broom, which I've already loaded here, we'll start as I just mentioned, we'll start by simulating X. So I've already got this typed out below, but for now at least, things might get crazy later and I'll have to just copy and paste, but I think there's value in doing it from scratch. Oh, was that all?
Sorry, just could you zoom in the screen slightly so we can read the screen? You can do, yeah, Sarah's just said Control and plus will zoom in for you, so it just makes the text a bit bigger.
Is that enough? A little more?
That's the one, a little bit bigger, maybe.
What's that?
A bit more there. That's legible for me. About everyone else. Obviously, don't want to assume that my eyes are the same as everybody else's. That works. Okay, great. Thank you very much. Cheers.
Great. Okay, so let's just generate a value of X, and here I want to put that into a data frame, and then later when we calculate Y, we'll be able to just add on to that data frame. So let's create a data frame using the data.frame function, and we'll call it, I'm just repeating what's typed below, but you can see in real time here, our X variable equals R norm. Whoops. And I'm just assuming, let's simulate 100 cases here with a mean of 5 and a standard deviation of 1. So if we run that, we get more output than we know what to do with. That's just printing the data frame. So we're going to assign that data frame to an object that we'll call simulated data. And there we go. So now we have 100 values of X. So that, I'll just retype what we did there. So now we can update this data frame by calculating Y. And rather than retype this like I just did with X, I think it'll be maybe more efficient if I walk you through step by step what's going on here. So we're taking the object we just created and we're reassigning it based on these additional commands on the right here. We're using the pipe operator from the tidyverse, which says we're going to take simulated data and then mutate a new variable. So mutating is just like computing a new variable here. So We're going to call that new variable y. We could call it anything, but y is convenient. And here, it looks like this, I actually want to be 2.8 to match our predicted regression equation. So 2.8 is our constant. And then for each person, we're going to multiply their score on X, which we simulated up here, times 0.21. And then we're going to add noise around that. The average amount of noise will be 0, with a standard deviation of 0.74, which creates those residuals like we just saw a moment ago in the slides. So I'll run this, and we now have two variables in our simulated data set. We have an X variable and a Y variable. And so we can take a look at this using ggplot. And hopefully you can see here we have 100 simulated cases. We've done it. We've simulated a data set. We could go ahead and analyze that. So we could create a linear model predicting Y from X using our simulated data. And we'll summarize that linear model, and it will tell us in this particular case, our intercept was 2.53. So this is noisy, so it's expected to deviate from our entered intercept of 2.80. And our observed slope is 2.6, which again deviates from our entered parameter of 2.1. And the residual standard error here is pretty similar to what we input, 0.74, happens to be 0.75 in this case. That's the way the cookie crumbled. All right, so we've got a data set, and we know how to analyze it. So we're off to a good start. Now we could do that 1,000 times and write down the answer, but we don't hate ourselves. So instead, we're going to use a more efficient approach. So let's go back to the slides to illustrate what this would look like. So we've done the parts on the left here, simulated a data set and analyzed it. Now we need to create an easy way to do that again and again and again. And the approach I'll recommend here is that we create a function that simulates just one data set. And then we use that function within a second function that creates a loop to do this as many times as we'd like. It's a little abstract, so we'll go through it. So let's start by looking at the code that we just used to generate values of X and Y. Here, actually, I'm noticing again that I'm missing some questions, so I'm just going to try to address these before getting into what's about to happen. So share, zooming in on the code. How do you make sure that your sample size estimate is not biased because your pilot data overestimates the effect size? That is a real worry. That's a real worry. One answer would be to run a bigger pilot, but that sort of undermines the point. How much bigger? We'll do a power analysis. Oh no, we've gone in a circle. Another approach would be to be extra conservative. Yet another approach would be to work backwards from a smallest effect size of interest. If you're willing to designate, this is easier when you're dealing with units that are more meaningful than psychological Likert scales. But if you're willing to plant a flag and say anything smaller than 0.1 changes in happiness, for example, anything smaller than that, I don't care about, so I'll power to that. That's a concern. I wish I had a better answer to it, but for now, we'll focus on the how of how to do it. All right, let's see what else I got. It's often recommended to take a fraction of the, use the lower confidence value. Yes. Oh, another approach that these are reminding me of, and this might be, you can also run this process in another way to figure out small size if you have, good suggestion, Lisa. Finally, one more approach I'll throw out there that kind of is very different than what we're doing here is to work backwards from a desired precision of your confidence intervals. So you can say, I'd like to predict the value of the slope within a certain range. And through simulation, we won't go anywhere near it today, but through simulation, you could compute width of confidence intervals and see how that varies as a function of sample size, and pick a sample size that provides a satisfactorily narrow confidence interval. Okay, so back to how to do this. Okay, so so we're going to take is the code we've used to generate a few variables here, and I want to turn this into a function. I want to build our own function that we can use as a tool to generate any sort of data set that we'd like, turning any knob up or down at will. So you can see that there's a couple of factors that we want to play with here. We know there's our sample size. So there's n equals 100. We use that both in our x variable and our y variable. We might want to make our constant bigger or lower. We might want to change the slope of our line. We might want to change the degree of the amount of error. Well, we can create a function that allows us to input any of those as arguments and produce a data set that has those properties. So here I'm showing in color here the different values we might want to tinker with. So we can put this code inside of a function, and running this will return to us an object called sim.dataset. And sim.dataset is our new tool. We can use this tool to generate data sets. And for each data set we generate, we can input different values. So say you want a data set with 30 cases and the parameters matching the sample data, the hypothetical pilot data and normal degrees of error. Well, we can use our new tool to generate that. Or what if we want a bigger sample? Let's say 300 cases. Well, here we can generate a data set with 300 cases. Why stop there? 3,000. We can make the line go away. We can entertain the possibility of a flat line that should only be significant 5% of the time, and those are false positives. We can play with the slope. We can go in the opposite direction, make the slope 4 times as big as it was a moment ago, and change our intercept accordingly. We can also tinker with the degree of error. So we've made a pretty cool tool here, or we're about to. Let's head over to R to build our function. And along the way, I'll take a look at questions. Looks like good resources being posted in the comments. And sharing the screen again. Okay, so as I've mentioned, I don't think we've made a function in here yet, but the idea behind the function command is that we, at the top here, we designate arguments that we want to be able to enter and customize once our function is created. So before, recall that our value of n we entered manually as 100, but we'd like that to be any value. So here we're using the symbol n to represent the spots in our code below where we'd like the number to be used. Same for our intercept and our slope and our residuals. So when we do that, we ask our function to return the data frame that these commands produce. We ask our function to return that. And so what this provides is our new tool. So up here, we now have this function called sim.dataset, and we can try it out. So I'm just going to ignore the code below here. So our function is called sim.dataset. So let's just create a data set called test_dataset. And we will use the function sim.dataset. And we have to enter values for each of the arguments that we designated. So n, let's say, I hope I'm not interfering with anything below. So I've already done this. So why don't I just copy this over and And we can look at these as reasonable values for our test data set here. So we're gonna say, let's generate 150 cases using the parameters from our pilot data into an object called test_dataset. And when we do that, we have a data set. And you can see it has 150 observations, which is exactly the number indicated in our argument here. And we can take a look and see for these 150 cases we generated, how do X and Y look? And sure enough, it appears that they're related to about the degree that we'd expect based on what we put in here. And of course, we can analyze this as well. So here I'm creating a linear model and summarizing it. And in this particular case, our estimates vary about the amount you'd expect. They happen to both be significant here. So this is good. We've got a data set that's useful, but of course we want to be able to do more than just look at one data set. So back over to the slides. I hope no one's getting dizzy from all the switching. Thanks for being patient here. Okay. So we've created one function that creates one data set. Now we want a function to loop that data set many, many times and aggregate those results into a summary. That's our power. That's what we're here for. So so let's take a look at the sort of the logic behind what this second function would look like. So we will use a for loop to do this many, many times. And just like we did before, we want to be able to tinker with different values within this set of code. So if we were to run this once, we could compute the mean for power. We'll get into what this means when we go to the code. But we could one time for 1,000 simulations produce an estimate of the power for our slope. That's great, but what if we want to be super diligent and use 5,000 simulations? Or what if we want bigger data sets or shallower slopes? So we can wrap this all into a function that allows us to tinker with each of those individually. And just like we did before, we indicate the arguments that we want control over. Oops, and here, these purple 1000s should be the symbol n.sims to indicate that within our function, whatever we input for a number of simulations will be used in the code below. But whoops. Sorry, so when we run this function, we create a function that returns a summary data frame for us that'll show us our estimated power for each of the coefficients in our model. And that is a second tool. So this new function that we've arbitrarily named simulate.power, that's a tool that we can use to run simulations with as many simulations as we'd like, and a data set that has whichever properties we'd like. All right, now we can calculate some power. So in this example, we say there's 100 cases and we'll run 1,000 simulations with a really big slope here. It seems wrong. I think this should be 0.21, especially with that power. But in any case, the broader principle here is we could slowly turn up the sample size. We see power goes up when we run bigger samples, which is really convenient. I'll also point out here, I've constructed this code, we'll look at it in R, to also return the power for the intercept. That's usually not interesting either in our analysis or in our power analysis. I'm including it here so that we can scale up more easily to multiple regression, where we really will want to return several different parameters power. Okay, so this is a little abstract. Let's go back over to R and actually do this. And as usual, along the way, I'll stop and see if we have questions. I'm always wondering about ads. So what about adding several random effects by sampling participant intercepts and slopes? I'm too new to this, but wonder whether this would improve the prediction of the power as it matches the analysis better, but maybe it doesn't even make sense. Yes, maybe people can comment in on this. It's absolutely possible. It's beyond the scope of what I'm tackling today, but you can run mixed models. You can run power for mixed models with simulation. Absolutely, that it can be done. And so I'll let others comment in with more details there. Okay, so back to a simple regression case. Okay, so here, before we build our function, I just want to illustrate what a loop would look like if we're just doing a single loop with values that we're comfortable with. So forget about creating a tool that lets us tinker with all these different knobs. Let's just run one power analysis that we care about. So here we could say we want to run 1,000 simulations, but I'm going to change it to 500 for time. But even then, who knows? We'll see. Hopefully this doesn't get boring. So we're going to use a for loop to run through 500 iterations and return the average power from that. But we're going to need an object to put those iterations in. And so we'll create an empty data frame with two columns. One column to store the results of each iteration for the significance of the intercept, which we don't really care about, but I'm including here to be comprehensive. And also a column to hold the results for the slope, which we really do care about. That's why we're here. And so we're going to assign this to an object named coefficient.power. And you can see this is just a big, lonely data frame of 500 empty rows ready to store the results of our for loop here. So in our loop, we are for each of 1 through 500, we're going to simulate a data set based on these raw parameters that we're entering here. We're going to assign it to an object called simulated data frame within our loop. And here's where we use the tidy package to make things a little simpler. So let's look at one example, and then you'll see more clearly, hopefully, what the for loop is doing. So if we take just one data set, let's run a linear model for our hypothetical simulated data set, and we'll call this model. All right, so we have what did I do here? Oh, we'll call it test data set because that exists. Okay, so we have a test data set and we run a model for it. We've saved it as an object. We could summarize the model, and that gives us summary. And that gives us a lot of output, but not in a terribly convenient format here, especially when we're trying to save specific p-values. So instead, from the Broom package, we can use tidy, which gives us a neat little small tibble or data frame with rows and columns, a row for each term that we're interested in, and columns for the estimate itself, standard error, statistic, and of course, what we're really interested in here is the p-value. Now, within that model, we can look at just the p-values, which is great. So here we've got on the left the p-value for our intercept for this one simulated data frame. On the right, we have the p-value for our slope for this one simulated data frame. In our loop below, we're going to want to look at them one at a time. And we can do that by indexing here, I believe the term is, 1 for the first row, or 2 for the second row. And in this case, the first row is our intercept, and the second row is the slope of x. So that is what's happening below. And for each iteration through, it is updating our object coefficient.power with the results of that iteration. So when we run this, we now have a very different coefficient.power. Now, instead of an empty data frame, we have trues and falses. So it's been filled in with the results of our simulations. Should mention here with the p-values, I asked it to evaluate whether or not it's less than 0.05. And conveniently, that returns true and false, which you can take the mean of, and that gives you power. So that's a lot. I realize that. I'll see if there are any questions before I wrap that up into a function. Okay, so here we're going to create a function that will produce a tool that lets us do this with a single line. Oh, whoops, let me share again. A function that lets us just change these however we like. So we're going to keep the same arguments we used before. We'd like to be able to change our sample size. Obviously, that's central to power analysis. And we might want to entertain different model estimates and degrees of error. But the new one here is the number of simulations. So we'll call that n.sims. And so when we run this function, we will be able to specify any number of simulations that we like. So we now have, I've called this function simulate power. And we can use our new tool to simulate power. So let's calculate power with 500 simulations. And let's assume a sample size of whatever I did below when I mapped this out ahead of time. Let's say 100, but this could, of course, be anything, and we'll want to play with it. We could even make a power curve equals 100, and I'll just copy over the same parameters we've been using suggested by our pilot data, but of course we could tinker with these. And this will return for us a summarized data frame showing the power for our intercept, which we don't really care about, and the power for our slope. So we can see for our intercept, in every case, the intercept was significantly different than 0. Okay, that's whatever. But the power for our predictor x variable here is about 79%. So 79% of the time under these assumptions with 100 participants and these assumed model parameters, we'd have 80% power. Okay, 80%, is that good? I don't know, depends on how much risk you're willing to tolerate. There's a lot of wisdom in not settling for, 80%. So let's just say we have resources to run not 100, but 200 people. And we want to know what is the probability if we run 200 people that we're going to walk away with a significant result. So we can run this again. And also assuming these same estimates, now our power is up to 98%, much more comfortable. So hopefully you realize that we can change much more than just the sample size. Suppose that we worry, like one of the questions suggested, maybe we're worried that our sample was so small that we happen to draw a really optimistic estimate of the slope. And we want to be more pessimistic. Let's just reduce the slope in half to just 0.1. The slope was 0.2. Let's assume it's 0.1. That's going to be harder to detect. Again, assuming 200 participants, well, that would provide only 50% power. So we're really not well powered to detect an effect a slope that's that shallow. You could tinker with the residual standard error. So say your pilot data, I don't know, here's an example, but I don't know how well this maps on empirically to the way studies actually work. But let's imagine that your pilot sample was collected in the lab free from distraction. So let's speculate that you got especially error-free responses. People were able to focus undistracted, but your real study is going to be online. And you might suspect that online is going to add is going to add more noise to your estimates. So instead of 0.74, let's just call this an average error of an entire scale point. So we could run that, but let's go back to our initial parameter of 0.21. So we can see we're going to have more noise here. So compared to our earlier power of 0.98, here with this extra noise, our power is down to 0.85 if we think that the average residual is going to be around 1. So you can do a lot. We've got a really cool tool here, so we can finally calculate some power. All right, so I'll pause here, see if there are any questions before we scale it up to bigger designs. Okay, sorry, I'm sort of a slowish reader, but I'm processing here. It's great if you can run a pilot, but how can you estimate parameters when you don't have pilot data? Secondary analysis, where your max sample size is known. I've done an extensive lit review where the means and SDs are not too difficult to find, although it can be a pain as well, but the intercepts and standard errors of the residual are difficult to estimate. Do you have some tips on how to approach this? Right, well, yes, this is difficult. I don't, off the top of, you may be able to work backwards from the means and standard deviations, and if correlations are reported, you might be able to work backwards from those as well, though on the fly, I'm not able to tell you exactly how that math would work, but if you have the standard deviations, almost certainly that's related to your residual standard errors somehow. For an independent variable, so for Kadia's question, how would you go about running a power analysis for an independent variable with multiple time points? Oh, good. Yeah, Lisa, that resource looks helpful. Kadia, you're asking sort of about repeated measures, and depending on the design, you might look at a mixed modeling, which could be done, but is more complicated. Or if this is something that could be done with a simple repeated measures ANOVA, then there are other packages that handle that differently. So there's that. Oh, and of course, FO, yes. The marvelous FO package. Okay. Let's scale up. So we're using regression because it's flexible, because it can accommodate many predictors. Well, let's look at a hypothetical example where our predictors, where we expect an interaction. Okay, so in our example, we are supposing that self-esteem predicts happiness. Let's hypothesize that the degree to which self-esteem predicts happiness depends on some experimental manipulation we might introduce. So suppose that and again, I am making this up. I don't know how reasonable this is, but it's a convenient example. Let's say that we believe self-affirmation should increase happiness, but this could vary as a function of self-esteem. So let's imagine that people with high self-esteem have a lot of good things to say about themselves. So randomly assigning people to a self-affirmation exercise should be especially effective for people who have high self-esteem because they have a lot of nice things to self-affirm about themselves. For people with low self-esteem, maybe not so much, or framed alternatively, self-esteem may not predict happiness as well when you haven't reflected on self-affirmations. Maybe it predicts it more strongly when you have. Forgive my haphazard theorizing here. I'm just trying to establish a basis for an interaction design. So to actually test this in regression, we're just going to scale up our equation here. So instead of one predictor, we're going to have three predictors. We're going to add a term for our new condition variable where people are randomly assigned to a control condition or an experimental condition. And we're going to add an interaction term that is the product of X, the self-esteem score, and W here, the condition that people are randomly assigned to. W we're going to represent a dummy coded with 0 for the control condition and 1 for the intervention condition. All right, so mindful of time here, I'm just going to briefly remind ourselves what parameters represent when we have an interaction design in regression like this. So now with this design, assuming that we've centered our predictor X variable, which we'll do in our simulations that eases the interpretation here. If we've centered it around the mean, our new mean is 0. And what that means is that our intercept is the predicted value of happiness for people who have an average level of self-esteem and who are randomly assigned to the control condition. So when X and W both equal 0, this is the value, the intercept is the value we would predict for those folks. Now, our first slope here is the predicted change in Y for a 1 unit increase in X when W equals 0. That's the slope for our control condition. Now, this would change if we were to change the coding of the intervention versus control condition. If we reversed it to 1 and 0, our interpretations would change. But here, I've designed it this way deliberately so that our control condition more or less represents the hypothetical simulation we just ran. This new coefficient is represents the difference of our conditions when X equals 0. And because we centered X, then this means at an average level of self-esteem, what is the difference between our control condition and our intervention condition? And finally, our interaction term is the predicted change in the slope of X for a 1 unit increase in W. Now, because W only has 2 levels, a 1 unit increase in W is the difference between our control conditions slope and our intervention conditions slope. So we have these terms. If you're familiar enough with regression, you can interpret these terms appropriately and you're good to go. So you can start to imagine different predicted patterns of results that you would want to simulate power for. So let's try simulating power here. And we're going to take an approach very similar to what we just did in the simple case, but we're just going to need more parameters to get it done. We're also going to need to add a line to center our X variable, and we're going to use the sample function to randomly assign people to conditions of W. We'll handle that in R in a moment, but first, let's just remind ourselves of the magical power of simulation, where we first predict in a world without any noise the values of our model. So here I have computed Y based on the parameters from below, but with W added. Y is a function of X, a function of W, and the interaction between X and W, and some noise. Even with interactions, our model's not perfect. So here I'm depicting what would happen if the noise that you simulated was 0. So just assuming that you have perfectly accurate estimates, here's what you get. But again, we could slowly dial this up by changing the standard error of the residuals. Here's what it would look like if it was 0.50. And here's what it would look like if it was 0.74, which happens to be the value of our pilot data. So here's just one simulated example of this. So just like we did before, if we can do it once, we can do it many times. We'll just have to add some extra terms to the code to make that work. So let's head back over and see how that would operate. Okay, looks like there's more discussion there, but I'll just power along. I'll just power through here. Forgive that. All right. Okay, so again, we will start by simulating our predictor variables, and from those we'll calculate our dependent variable. So here, in addition to simulating X, which we'll do the same way we did last time, a mean of 5, standard deviation of 1, 200 cases, we also need to randomly simulate levels of W. And this is where we can use the new sample function. So sample allows you to, sample from a list of possible values. So here, the values that could be sampled are 0 for the control condition and 1 for the experimental condition. We want 200 of these samples to match the number of X values that we've simulated, and we want to sample with replacement. And we only have 2 values here, so, so we need to set replace equals true to be able to sample again and again and again from this group of either 0 or 1. And finally, after we do that, we're going to center our X variable by taking the mean of X and subtracting each score from it. That'll help the interpretation of our coefficients a little. Okay, so we can create this data frame and save it to an object called simulated interaction data. And now that we have this data frame, we can compute values of Y as a function of our simulated values of X with a given amount of noise. So here we're using the same intercept, the same value for X. Here I've just arbitrarily picked the difference between conditions at a mean level of self-esteem. Let's say they differ by about half a scale point. And let's say the difference between the slope of self-esteem in the regression or in the control condition differs from the intervention condition by 0.3 units. So the slope after people self-affirm, the relationship between self-esteem and happiness, it should be a stronger relationship. Let's say it's stronger by 0.3 units.
Like the debugging going on here, Andy. There's a point where you're taking away the value from the mean rather than the other way around. So line 130. Someone's just picked this up on the chat.
Oh, thank you. So it ought to be like so. Like so?
Yes.
Ah, thank you. Okay.
Jill, thanks, Jill.
All right, so we've simulated a single data set. Let's test it out. And here, a couple of the points are falling out of the range. That's a nuisance. We'll talk about that later when we're customizing. But we've got a simulated data set. So here it looks like the slopes are actually pretty similar to each other. That'll happen sometimes. Perhaps if we simulated a bigger data set, we'd have more accurate representations of the input parameters. But that's what happens when you're dealing with samples instead of a larger population. Okay, so as before, we can wrap this up into a big function to simulate a single data set. And here, instead of just n intercept and a slope for our x variable. We also have a slope for our w variable and a slope for our interaction term. And you'll see within here, we also have computing our variables accordingly. But getting that turned right. Okay. So we can create a function called sim.dataset for an interaction. And now we have a new tool again. So we can use this to create a test data set, but this time we're going to have to give it more information, of course, because it needs to know the intercept, the value of our x slope, but also the value of our w slope and the value of the interaction. So entering all of those and assuming the same amount of residual variance we've been assuming all along, we can create a single test data set called test.data. And this has 100 cases, but this is a bigger design. We recognize we're going to need more samples, or more participants. Let's just assume 300 cases. And so we can see how those data look. And here, I'm not sure how it's appearing with the resolution on your all screens, but you can discern the interaction that matches the parameters we entered. So for the condition corresponding to 1, which I'm saying will be the self-affirmation condition, we get this really strong slope. For the condition coded 0, the control condition, we get a shallower but still meaningful slope. So that's good. We can generate a single data set, but of course we want to be able to generate many data sets. And so we can do that using looping again, and also wrapping it into one big function that does many, many iterations. And as before, we've got the same arguments for the function as last time, but also we want to be able to tell it how many simulations to be able to run, so that we can tinker with that as well. Everything in here is a sensible extension of what we did in the simple case. So for example, you'll notice that our object to hold the results now has 4 columns. We need a column for the intercept and the slope of x, but also a new column for the slope of w and a new column for the slope of the interaction term. We have to save all of those from each iteration through this, and so we have extra rows below doing that. We also want to be careful to update these values here, which indicate which row from our broomed tidy object to be taking the values from. So just to quickly illustrate, if we create a model 2, I'll call it this, forgive the haphazard naming here. So we'll predict y from x and w with test data. Oh gosh, 2 L's in the model, come on. Okay, whoa, where'd I go? Okay, so now we can use tidy to look at model 2, and we've got extra terms now, which is good. We have a p-value for x, a p-value for w, and a p-value for their interaction appearing on the first, second, third, and fourth lines. So in our function for this, we are careful to request to pull the p-values from the corresponding lines. And this loop also summarizes the power into a single data frame arbitrarily called coefficient.power.interaction. And so when we run this function, it will provide for us just a nice little summary of the power for each of these terms. So I just created that function, and a new tool called simulate.power.interaction, and we can simulate some power. So let's assume we'll need 300 people, see how much power that gets us. Let's do 500 simulations let's do 200 simulations for time. And we'll use sort of the same regression terms. These are the slopes that that I've been entertaining earlier, but you could change these. That's the great thing about all of this. So assuming these parameters, what is our power with 200 iterations? We have problem. Perhaps this needs to be that. There we go. So in case you missed that, I had right here, I had a leftover, the raw value of number of simulations. But because I'm creating this function, I want to use just the symbol n.sims to refer to that throughout. So clean that up there, run the power for 300 cases. And for our, it's important to keep an eye on what these coefficients represent, but this B1 slope here is the effect of self-esteem in our control condition, and that's 0.94. B2 is the difference between conditions at an average level of self-esteem. That appears to have been significant on every single iteration through, so you're very likely to observe that in a study with 300 people. And finally, B3 here is the power for the interaction. So there you go, all at once. So we could change the sample size, we could play with the parameter estimates, the amount of noise, just like we did before. There you have it. All right, I'll turn over to the questions now and see if there's anything I can address. All right, well, thank you. Cool. So I'll open it up for any questions. I can also talk about a few ideas I have on customizing this, but you may be disappointed on, most of the ideas for customizing this come down to use the faux package.
Well, thank you very much. Cheers, Andy. All right, so yeah, so open up for some questions, and has anyone got anything they'd like to ask?
All right. Well,
yeah. Oh, sorry. So we've got someone asking for the customization. I'll shut up now.
All right. So I should proceed with some thoughts on customizing. Did I understand that correctly? Yes, please. Okay. So I won't belabor this too long, but a few. Well, actually, let me share. Few things you can do. So opening up some new examples. All right, so say handy thing to be able to play with is, what if you expect different group sizes? So say you're studying left-handed versus right-handed people and you expect only 10% of your sample to be left-handed. Within the sample function for generating values of a categorical independent predictor, you can use this probability argument that lets you assign, say, a 10% chance to the 0 condition and a 9% chance to the 1 condition. So that's handy to be able to do. Yeah, we could try that out, but I'm sure you trust that would do what it ought to. A few things that I don't have great solutions for, but are worth thinking about. Sometimes when you run this, you may have noticed as I was graphing some of these, we'd get notices that values would be out of range. And so the simulated values fell outside of 1 and 7. It's kind of a nuisance here when we're simulating power. I believe the faux package can handle that pretty elegantly. But in the meantime, if the best I've got is to clumsily basically Windsorize or take any case that falls outside of the range and apply the scale maximum or minimum to it. So you can do that using this. I can go ahead and post this after. What if your independent variables are themselves correlated? Again, using the marvelous faux package, it's easy enough to generate correlated independent variables. And skewed variables, also this function from the faux package, I think, can start to address that. I'm not certain how that affects the units, but that's at least a place to start in exploring how to introduce skew into the design. We had a question earlier about normal independent variables. This is a place to start to look at that. Okay, so let me look back over to the questions. Chat. Great. Okay, thanks for posting that. Okay, that's what I've got. Thank you, everyone.
Much, Andy. That's absolutely amazing, and great continuation of the theme. We're back on Friday with Sarah Chadwick, who's going to be discussing logistic item response models, which is I'm really looking forward to. And so I guess we'll see you all then. Thanks very much.
Everyone, bye.
Annie, can I chat with you a sec? Because you're not on Twitter, and we've been having a Twitter DM discussion among some of the people in this workshop who are on Twitter.
Oh, cool.
About putting together some of the materials into an online book, like a book down. Where did I put this book down? So there's already a demo. If you've got a GitHub.
Afraid not.
But even if you're not like keen on that, I've offered to help anybody who wants either just put their materials into a chapter. Like you've written all your stuff in an hour anyways, it would be really easy. You just write the paragraphs in between that kind of explain stuff, and we could link it to your the YouTube video of this, and I'll. Hey,
yeah. That sounds really valuable. I'm not sure where to get started. I mean, I could write a document that would do that, but it's like integrating it with I don't know, other technology. I need some help with that, but yeah, count me in. That's great.
Okay, so the I just put it in the chat, the link to that.
Okay.
And Ali, you'll probably like start helping organize the people who are not on that chat, but there were a fair number of people who were enthusiastic, so I thought it'd be an idea to go ahead and have a place to kind of dump tutorials on simulation, because people like are really keen to do data simulation.
Yeah,
really a one-stop shop for it.
Yeah, and with R Markdown, basically everything you've done so far could just be put into an R Markdown document as it is, basically, and it would compile nicely into an HTML kind of format, and then we can just add some little descriptions on the page, and yeah, it would be it's fairly trivial to do that, I say.
Sure. Yeah, I'd be very happy to do that.
Wonderful. Okay, great. Thanks so much. I'll get in touch with you by email and CC Lisa in as well.
Perfect.
This was really fun. Thank you. I love watching how other people teach this stuff.
Yeah.
I know, it's fun. Yeah, amazing. Yeah.
All right. Bye.
Thank you very much. Bye now. Bye.
Cool. All right. Well,
cool. I'll drop you an email about that. And thanks very much, Andy. Cheers. Thanks again.
Good. Thank you.
See you again.
Bye.
Bye.